All right, ladies and gentlemen. So this will help you. We need to go back. You take out your notes and look at page 7, example 3, so that you can go back and do that one problem for homework that was due tonight. So again, here we have a piecewise function, and in the piecewise function we have a rational function, and graphically, x equals 3 graphically would represent what? If I was to know that y value, graphically, what would this represent? This would represent a what? A line. What does the equation of a line look like? Y equals mx plus b. I don't think that looks like y equals mx plus b. This is a single point. So they want us to find k so that f of 3 is equal to the limit as x approaches 3. Well, first of all, f of 3 is what? F of 3 is your defined value. So we want to assure that the defined value at x equals 3 is equal to the limit. Again, this is a two-sided limit, so what's coming from the left is equal to what's happening on the right. So obviously there's something happening at 3. So we got to figure out graphically what is happening at 3. So look at this rational expression of x squared minus 7x plus 12 over x minus 3. Now, can you factor the numerator? The numerator factors into what? X minus 4 times x minus 3 over x minus 3. And what do you notice at x minus 3? You can do what with that factor? You can cancel it. So graphically, what's happening with this rational function at x equals 3? You have a what? Hole. We have a hole at x equals 3. So now remember, when you have a hole, you simplify your fraction. So really what you're looking at is you're looking at the equation y equals x minus 4 with a hole at this particular single point. And what is the y-coordinate for this particular hole? The y-coordinate's what? It's -1. So graphically, again, graphs are going to be your friend. What does the graph of y equals x minus 4 look like? That is a what? If I was to graph, it's a line. Y-intercept is what? -4, and the slope is 1. And then again, we have a hole at 3, -1. So that's really what is happening with the first part of the piecewise function. Yes, Baruch? How do you find the y-coordinate? You agree the x value is 3, okay? But remember, you find the y value by taking the value and plugging it into the simplified form. All right, so now let's talk about how we can find k so that the defined value would be the same as the limit as x approaches 3. Well, look at the sketch that I gave. The limit as x approaches 3 is going to be the same as the y-coordinate of the hole, isn't it? So the limit as x approaches 3 is going to be the same as the y-coordinate of the hole, correct? So how can I assure that the defined value would be the same as the limit? What am I going to have to do? I have to fill in the hole. So what is the k value going to have to be? What is k going to be equal to? Well, what's the y-coordinate of the hole? The y-coordinate of the hole is what? -1. Draw your pictures. I can't emphasize that enough, to draw your pictures. Now, once you fill in the hole, the limit as x approaches 3 from the left and the right is the same as the defined value. All right, any questions on that? So now, with k as the assigned value, and the limit as x approaches 3, show that f of x can be expressed as a polynomial. This is your polynomial. Remember, lines are polynomials. What is the equation of this line? The equation of this line is simply what? Y equals x minus 4. Now that you filled in the hole, this is now what this graph represents. It's just this equation of your line once you fill in the hole. With the hole, it's back to the original expression. All right, so any questions on example 3? Yes, Mary?
So is k always
For this particular problem, yes, because there is the hole in it. Yes, for this particular problem, yes. All right? All right, so now let's go on to some more limits. So let's talk about, and you've actually done this, believe it or not, when you were introduced last year to end behavior and horizontal asymptotes. You were actually doing limits at infinity. So what you've been looking at so far is you've been looking at limits as x approaches some real number. Like x approaches 5, x approaches 6. But suppose instead of approaching a number, it's going to approach infinity. So the limit as x approaches infinity of f of x. Or the limit as x approaches negative infinity of f of x. So what we're going to look at in this particular section is what happens when the limit x is not approaching a number, but it's approaching infinity or negative infinity. And with this, you've actually done it. You've actually done it. Last year back in Algebra 2, your Algebra 2 teachers asked you quite a bit to find end behavior, did they not? They asked you to find horizontal asymptotes, did they not? What you were actually doing is you were finding the limit as x approaches positive and negative infinity without being introduced to the limit idea. So when you have the limits as x approaches positive or negative infinity, what you're looking at is you're looking at the end behavior. That's what you're looking at. One of three things can happen when you're talking about the end behavior of a function. The graph could be pointing up. What would we say if the graph was pointing up? Would be going towards what? Positive infinity. So one answer could be positive infinity. If you look at the end behavior, it's pointing down. It would be going towards what? Negative infinity. Or if there's a horizontal asymptote, the end behavior is approaching a horizontal asymptote. So when you're asked to find the limit as x goes to positive or negative infinity, it can only be one of these three things: positive infinity, negative infinity, or a horizontal asymptote. All right? So let's take a look at this particular graph here. Find the limit as x approaches infinity. So what side of the graph are we looking at? We're looking at the end behavior on what side of the graph? Well, where are all your positive x values? On the right. So on the right-hand side of this graph, is the graph pointing up, is it pointing down, or is it approaching a horizontal asymptote? Horizontal asymptote, what is the value of the horizontal asymptote? 2. So there's your answer. Take a look at B. The limit as x approaches negative infinity. We're looking at what side of the graph? We're looking at the left. So on the left-hand side of the graph, again, we're looking at as x approaches negative infinity. I don't care about what's happening around the origin. What's happening is these x values get really, really small. Is the graph pointing up, down, or is it approaching an asymptote? Asymptote is approaching what? Negative 2. All right? So like I said, when you're looking at, again, it's when you have the x approaches positive or negative infinity, you're looking at the end behavior. All right? Not all graphs have asymptotes. So that's where you need to remember all the different study of all those different functions from Algebra 2 and the end behavior. So again, here is a polynomial function. Remember, what dictates the end behavior of a polynomial function? What do you look at? You look at the largest what? The largest exponent for x, correct? That dictates the degree of the polynomial. What is the degree in 2a? The degree of the polynomial is what? 3. And then you have to look at the leading coefficient. Is the leading coefficient positive or negative? Positive. So now you have to remember your end behavior of polynomial functions. If you have an odd degree polynomial function where the leading coefficient is positive, remember the graph looks something like this. If your net leading coefficient is negative, remember it will switch the end behavior. Bringing it out a little bit. So now, limit as x approaches negative infinity. What side of the graph am I looking at? The right or the left? Left. So what's happening on the left-hand side of your odd degree polynomial functions leading coefficient positive? Going towards what? Negative infinity. So remember, if there's no horizontal asymptote in the functions, you've got to remember what the end behavior of all the different functions you study. All right, let's look at P. Limit as x approaches infinity. What is the degree of this particular polynomial? The degree is what? 6. Is the leading coefficient positive or negative? Negative. So you have an even degree polynomial function with leading coefficients negative. What happens to the ends? They point down. Remember, it's going to point down. So again, we're looking on the right-hand side. So what's happening on the right-hand side of this graph is going towards what? It's going towards negative infinity. So again, if you're asked to find the limit as x approaches positive or negative infinity of polynomial functions, you've got to remember the end behavior. All right, there's no horizontal asymptote, so your answer is going to be positive or negative infinity. All right, any questions on that one? All right, we talk about rational functions. Well, as you know, rational functions have horizontal asymptotes. So if I'm asking you to find the limit as x goes to positive or negative infinity of a rational function, all you do is find the horizontal asymptote. Yes, Mary? You mean that's right here? Yep. Yeah, x to the 7th, x to the 9th, as long as the degree is odd for polynomial functions. Now, the only way it would change is if the leading coefficient is negative. So in other words, if you have a leading coefficient that's negative and it's an odd degree, the end behavior switches. It'll look like this. So whether like it's a negative x to the 3rd, a negative x to the 5th, a negative x to the 7th, the end behavior will change. Okay? So like I said, if you have a rational function, you're going to define the horizontal asymptote. Again, a function can have at most only 2 horizontal asymptotes. What makes a horizontal asymptote? It is the limit concept. It is the limit as x approaches positive or negative infinity. Some of you, when we were graphing rational expressions, were asking about how can a graph cross a horizontal asymptote? It can. The true definition of a horizontal asymptote is a calculus definition. It is the fact, if we don't care about what's happening around the origin, we care about the behavior of the function as your x values get really, really large. So as x goes to infinity, is it leveling off? Is it approaching a fixed number? Or as x is getting really, really small, is it approaching a fixed number? I really don't care what's happening around the origin. Those are not your really large x values or really small x values. Still satisfies the definition of a horizontal asymptote. It's still approaching a fixed number as your x values get really small in this case. All right? So again, to review, here are all your rules for finding horizontal asymptotes. Remember, if the degree of your numerator is less than the degree of the denominator, your horizontal asymptote is 0. If the degrees are the same, you have to look at the coefficient of the numerator and divide it by the coefficient of the denominator to make that ratio. Remember, if the degree of the numerator is larger than the denominator, there is no horizontal asymptote. Your answer will be positive or negative infinity, and what you have to do is you have to look at the graph. Yes, there's a slant asymptote, but again, the slant asymptote is not affecting the end behavior. All right, so your answer will be positive or negative infinity, and you have to look at the graph in order to figure out what's happening. So let's take a look at example 3a. So tell me about the degree of the numerator when you compare it with the degree of the denominator. Less than. So the degree of the numerator is less than the degree of the denominator. So when you're looking at the limit as x approaches infinity, since there's a horizontal asymptote, the end behavior is simply going to be the horizontal asymptote, which in this case is simply going to be what? 0. So all you have to do is find your horizontal asymptote. Here's another rational expression. Again, the limit as x approaches negative infinity. Look at the degree of the numerator and compare it with the degree of the denominator. Tell me about the degree. They are what? The same. So then what's the horizontal asymptote going to be? The horizontal asymptote will be 3 over 2. And that is your end behavior. That's the y value that the graph is approaching as x gets smaller and smaller. Now let's look at C. Tell me about the degree of the numerator when you compare it with the degree of the denominator. It's greater than. So is there a horizontal asymptote? No. So there's no horizontal asymptote, so the end behavior is not approaching a horizontal asymptote. So the answer is going to be positive or negative infinity. So I'm looking at my x values as we go to positive infinity. So if you think about the graph, we know there's a slant asymptote somewhere. Doesn't matter where it is. Where are your vertical asymptotes? We'll look at the denominator. Your vertical asymptotes are going to be where the denominator is equal to 0. So I can factor out an x. That's going to give me 2x minus 5. So the vertical asymptotes are going to be where? The vertical asymptotes are at x equals 0 and where else? 5 over 2, which is 2.5. So it appears that this graph is probably going to be approaching positive infinity. To verify that my y values are all positive and going towards infinity, all you need to do is plug in a y value to the right of the largest vertical asymptote. Here's my vertical asymptote at 2.5. So if I plug 3 in to my original equation, I can verify what's happening with the y values. Are the y values going towards positive infinity or are they going towards negative infinity? Well, if I plug in 3 here, 3 to the 3rd is 27. plus 18, 27 plus 18 is 45, right? Yeah, 45 plus 1 is 46. Over 3 squared, which is 9, 9 times 2 is 18, and 18 minus 15 is 3. So when x is 3, the y values are going to be 10 point something. So remember the graph, what it looked like when we sketched them, looked something like this. So now look at the behavior. Is this going to be going towards positive infinity or negative infinity? Positive. So any questions on finding the limits of rational expressions? All right. Just a quick review, going back to algebra. Every number has how many square roots? 2. So when I ask you for the square root of 9, however, most of you just tell me what? 3. What's the other one? Negative 3. Typically, we just say the primary square root, which is the positive one. But don't forget, every number actually has 2 square roots. So we ask you about the square root of x squared. It's not just x. It could also be what? This could also be x, or it could be what? Negative x. So when you look at the graph of square root of x squared, it looks a lot like the absolute value function. So when you look at the square root of x squared, it looks a lot like your absolute value function. Because when you look at the graph, as you told me, the square root of x squared can be positive x, which is right here, which looks a lot like your line y equals x until you get to 0. Or it's going to look like y equals negative x. So here is what the line y equals negative x looks like until you get to 0. All right? Now, the reason why I'm bringing this up is, as you know, by looking at the graph, as x approaching positive or negative infinity, the end behavior is both positive and infinity. But when you're dealing with rational expressions that may have a radical in them, if you're approaching negative infinity, so if I'm asked you to find the limit as x approaches negative infinity, are these x values positive or are these x values negative? Negative. As x approaches positive infinity, are these x values positive or are these x values negative? Positive. So you agree with me when I asked you to do examples 3a, did I care about the 7x or the 2x squared or the 1 or 3 when I was asking about the horizontal asymptote? No, what's dictating the horizontal asymptote is the largest exponent for x in the numerator and the denominator. I can disregard everything else, can I? It matters. So now when I come down here, I'm still going to use the idea of horizontal asymptotes. But now I have to look at the limit as x approaches infinity. I've got the square root of x squared. This minus 1 doesn't matter. You have to consider now, is this going to be a positive square root or a negative x value? I'm on the positive side of the x-axis, so when I take the square root of x squared, would it be a positive x or a negative x? Positive x. So really what I want to look at is the limit as x approaches infinity of x over x. Tell me about the degree of the numerator when you compare it with the degree of the denominator. They're what? They're equal. So what's the limit as x approaches infinity of x over x going to be? 1. Look at B. The limit as x approaches negative infinity. Now I'm on the negative side of the x-axis. So when I take the square root of x squared, would I consider positive x or negative x? Negative x. So I have a 2x over negative x. So what is 2x divided by negative x? Negative 2. Again, the degrees are the same, so I know it's just going to be 2 divided by negative 1. So again, when you're dealing with rational expressions that have radicals, and you're doing limits as x approaches positive or negative infinity, it matters what side you're on, which square root you're going to use. Does that make sense to you guys? So look at letter C. So if I want to find the limit as x goes to infinity, by the way, what is the degree of the numerator here? The degree of the numerator is what? 2. So I'm going to consider the negative 5x squared. Over. I'm on the positive side of the x-axis. When I take the square root of x to the 4th, is it going to be positive x to the 4th or negative x to the 4th? Positive. It's going to be positive x squared. So what's the horizontal asymptote going to be for C? -5. Okay? Another type of problem that you have to be careful of involving radicals, even though it's not a rational expression, don't assume that this is just immediately going to go to 0 because the square root of 9x squared is 3x and 3x minus 3x is 0. Alright? What you still have to do is you can make this a rational expression by multiplying by the conjugate of the numerator. What is the conjugate of the numerator? Yep. So when you're dealing with radicals, as you're going to infinity, and it's not a rational expression, you're going to make a rational expression to help you figure out what's happening with this limit as you go to infinity. Again, when you multiply a binomial, it's conjugate. What's the square root of 9x squared plus x by itself? That's just going to be what? 9x squared plus x. Negative 3x times 3x is a what? Minus 9x squared. Over, and again, I have square root of 9x squared plus x plus 3x. Well, what happens with those 9x squares? They're going to do what? Cancel. Now you have a problem like we just did a few minutes ago. Again, we're on the positive side of the x-axis. So when I go to find this horizontal asymptote, I know I need to look for the largest exponent for x. Well, what is the square root of 9x squared? Would it be the positive 3x or the negative 3x? Positive. I can ignore this x to the 1/2. But notice there's another term that has a 3x to the first on the bottom. What is a 3x plus 3x? 6x. So what is this limit going to be then? This limit's going to be what? 6. All right, close to 0. All right, but not quite equal to 0. All right, any questions on finding the limits involving the radicals? And again, you can verify this using your calculators. All right, if you look at the limit as x goes to infinity of the problem we just did, the square root 9x squared plus x minus 3x. You can see it's getting really, really close to 0, but on your table, as these x values get really, really large, you can see that these y values are not approaching 0, they're approaching 0.1666. All right? So again, as I typed in these really large numbers, you can see that it's approaching that 0.166. Yes, Nina?
So I don't know, like how do you get from that number, like the one on the that?
Remember, what dictates the degree of the denominator is the largest exponent. Largest exponent is the square root of 9x squared. This x you can disregard. Just like up here, remember we did all the regular rational expressions? That's why I kind of mentioned this before. When you were finding horizontal asymptotes, did I even need to consider this negative 4x to the fifth or 3x to the minus 1? No. It's all coming from the largest exponent. Same thing with the radicals. Now, the only reason I had to consider the 3x that was outside the radical is because it turned out to be the same value of the exponent for the x when I did the radical. All right. But that's an x to the 1/2 underneath here, so you don't have to worry about it. Yeah, we're
So, like, before that was the minus
okay. Mm-hmm. Yep.
what happened?
It's the same idea up here. Did I care about the plus 4 here? No. What dictates it is the largest exponent. The exponent for 4, consider an x to the 0. That exponent is smaller than x squared, the square root of x squared. So what dictates, remember, the horizontal asymptote is the largest exponent for x. And that you can disregard anything smaller than that x, like the largest exponent for x. Does that make sense? Just like back up here, going back to the basic ones. we can ignore this x to the fifth, the 3x to the 1. It's not affecting what the horizontal asymptote is. You good? Okay. So your favorite, trig graphs. Now let's talk about limits as trig. Again, we're not doing as x approaches the number, we're looking at infinity. Let's talk about the sine of x. When we sketch the graph of sine of x, where does it start? Did it start at 0 or did it start at 1? 0. And then where it go? Max, which is up here at what? 1. And then it goes to what? Baseline, and then it goes to -1, and then back to your baseline. So remember, there's one cycle for your sine of x. And what happens with this graph as x goes to infinity? It just repeats itself. So what y values, what's happening with the graph? It's going back and forth between what two y values? -1 and +1. We call that an oscillation. It oscillates between -1 and 1. So when you have a graph that's going back and forth between two y values, we call that an oscillation. It's bouncing back and forth between -1 and 1. So when you have this oscillation, and I ask you to find the limit as x approaches infinity, this limit does not exist. Because it oscillates. It's going back and forth between -1. What would happen with cosine of x? Would cosine of x also have the same oscillation? Yes. So it does not exist as well. Again, just as the limit as x goes to infinity. Okay? Let's go to C. We'll come back to B. We'll use our calculator. Let's take a look at C. Limit as x goes to -infinity of inverse tangent of x. So now you got to remember what the graph of inverse tangent of x looks like. Well, hopefully you remember what the graph of tangent of x looks like. Tell me about the graph of tangent of x. What kind of asymptotes do you have? Vertical. Where are your vertical asymptotes? -pi/2 and pi/2. So now again, remember, for tangent of x, this is what the graph looks like. If you know what the graph of tangent of x looks like, hopefully that will help you remember what the graph of inverse tangent of x looks like. Instead of having vertical asymptotes, you're going to have what? Horizontal. Remember, the x and the y values switch. So instead of having this point at -pi/4, -1, you have it at -1, -pi/4. 0, 0, then you have it at 1 pi/4. This graph actually comes up all the time in calculus. Having to remember inverse tangent comes up a lot. So now looking at this graph, what would the limit be as x approaches -infinity? -pi/2, because you have the horizontal asymptotes. We actually use this quite a bit. Remember, if you forget what the graph of inverse tangent looks like, hopefully you remember what the graph of tangent looks like. All right, now let's take a look at B. So remember, you can always do limits by using your tables and using your calculators. So let's take a look at what the graph of cosine of x divided by x is going to look like. So here's getting really close to 0, isn't it? So let me look at the values in my table to confirm if it's getting close to 0 or some other value. All right? So notice I typed in a large number for x because I want to know what's happening as x is approaching positive infinity. Again, when it's 100, I get this number. I even get a smaller number. If I type in 1 million, like I type in 10 million. What am I getting really close to? I'm getting really, really close to what? 0. All right? Your favorite exponential involved functions. Tell me what you remember, let's say, about e to the x. Does e to the x have a horizontal asymptote? Or 2 to the x, or 3 to the x, or 4 to the x? Your exponential functions, do they have horizontal asymptotes? Yes, where is it? 0. Remember, they have a horizontal asymptote at y equals 0. And remember, whether you have an e to the x, a 4 to the x, or a 5 to the x, the end behavior is the same. You have a horizontal asymptote at 0, and then it's going to increase without bound for all the parent functions. So this is why, if you've got an exponential function, the limit as x approaches positive infinity, remember you're looking at the end behavior of the right-hand side, is going towards positive infinity. But look what's happening in the limit as you approach negative infinity. You're approaching your horizontal asymptote to 0. All right? So anytime you're asked about limits of exponential functions, you've got to look at the end behavior as x approaches infinity. Now your favorite, your log graphs. Do you have a horizontal asymptote for log functions? What kind of asymptote for logs? Horizontal or vertical? Vertical. You run the graphs with something like this. So any logarithmic function, whether it's a log, a natural log with a base e, a base 10, a base 5, a base 3, the behavior of the graphs, the end behaviors are the same. So again, the limit as x goes to infinity, it's increasing to positive infinity. Now, we can't talk about the limit as x goes to negative infinity because this graph stops at the vertical asymptote. But the limit as x approaches 0 from the right is going down towards negative infinity as it approaches the vertical asymptote. Now let's take a look at this one. This is like a fun one. E to the x plus e to the negative x divided by e to the x minus e to the negative x. Unfortunately, it's not direct substitution because this is going towards negative infinity. So first of all, you want to rewrite and get rid of all these e's with a negative exponent. So how can I rewrite e to the negative x? 1 over e to the x. You have a complex fraction. How do you simplify complex fractions? Multiply everything by what? E to the x. What is an e to the x times e to the x? E to the 2x. Plus 1 over e to the 2x minus 1. Now remember, you have all those properties of limits. When you're asked to take the limit of a quotient, you could take the limit of the numerator and divide it by the limit of the denominator. You're trying to find the limit of a sum. Remember, your other property of limits is you can find the limit of e to the 2x, add it to the limit as x goes to infinity of 1, and add those two limits together. So let's talk about the limit as x goes to infinity of e to the 2x. It's negative infinity, I'm sorry. What can you tell me about the end behavior? Is that 2 affecting the end behavior? No, it's just a horizontal stretch of compression, isn't it? It's not affecting the end behavior. So what's happening on the left-hand side of your e to the x? Your e to the x is approaching what on the left? It's approaching what? 0. So this is going to 0. Remember, with the limit of any constant, it doesn't matter if you're going towards positive infinity, negative infinity, or a fixed number. And the limit of any constant is just itself. So the numerator is going to be a 0 plus 1. Again, we just talked about in the last problem, the limit as x goes to negative infinity of e to the 2x is a 0. The limit of any constant is just itself. So what is this limit going to be? This limit will simply be what? Negative 1. So don't forget about all those properties of limits. Natural log of x squared divided by 3. So if you look on your calculator at this graph, take the square root of x squared. What this graph is doing, you're looking at the graph of x over 3, and this is x goes to positive infinity, but the left-hand side, you're looking at the limit as x goes to negative infinity of negative x over 3. And what happens graphically when you have a negative coefficient of x? It's taking your original graph and it's doing what with it? It's reflecting it where? Reflecting it over the y-axis. So that's where this graph is coming from. But is the end behavior the same? As x approaches negative infinity, what's happening with the direction? It's going towards what? Positive infinity. As x approaches positive infinity, it's going towards where? Positive infinity. All right? So the limit as x goes to infinity here is just going to be what? Infinity. Which is going to be the right hand. Again, looking at the graph, you can confirm that. But there's your limits as you go to infinity. So for a lot of these guys, especially your logs, your e to the x's, your trig, you've got to look back at the graph and look at the end behavior. All right, yes, All right, so ladies and gentlemen, your homework for tonight